it's on page 99. Page 99. All right, it looks like we're live, so we're going to go to chapter 12, page 99. Static equilibrium. All right, so if you have page 99 in front of you, this is a, whoops, there's that. Get rid of that. It's pretty gnarly, but it can be summed up with this. Whenever an object is not rotating and not translating, we say it is in static equilibrium. This is different from dynamic equilibrium. Dynamic equilibrium, you could be moving, but at constant speed. If you're moving with constant velocity. If you're moving with constant velocity, you would still have no net force, but you would be moving. That's called dynamic equilibrium. So static equilibrium means you're not moving, basically. All right. When that is true, we have these 2 bullet points. A lack of rotation implies sum of torque is 0. Otherwise, you would have angular acceleration and it would rotate. So that's basically a fancy way of saying alpha equals 0. Angular rotation rate or angular acceleration is 0. And notice, if you're not rotating about the top, the bottom, the left, the right. You're not rotating about any point. Okay. And then if your lack of translation, that means the sum of forces is also 0. So this is saying alpha equals 0. Let me just clarify that. This says alpha equals 0 about all points. And this one says A equals 0. And technically those are vectors, so I'll just slip that in there. All right. Okay. We've covered all the content for this semester. We could stop now. For real. Now, it turns out in real life, this seemingly simple topic is very, very, very hard. But technically, that's all the content. Yes, for sure, Nate Dogg. All right, so now look at this crazy procedure here. I definitely think you need to do a lot of problems for chapter 12, all right? 1, 2, 3, 4, not enough. You've got to do at least a dozen to really understand this one, okay? So just be aware of that one. No, it's once you do 10, 12 problems, you're like, it's very formulaic. And so let's go through the formula. That's what this page is all about. Number 1, you know how to do this already. Draw a picture, okay? Try to draw all the forces. And now this is something I don't want you to get lazy on me, people. Look at what I say in bullet B. It is often useful to draw a separate picture with lengths and angles and no forces. So remember, this is an FBD. Draw only forces. Do not draw the lengths. So no lengths. My apologies for the lag, as you said. And on the other one, I want you to draw the length and angles. And because this first step is so important to me, I want to emphasize it with a picture after I do part C. So if there's an actual pivot, don't forget there are forces at the pivot. Usually we write those as Rx and Ry. Before I go on, I want to show you an example from the solution manual, just exactly what I mean for bullet 1. This is huge. If you get good at bullet 1, everything else is easy, okay? Oh, not easy, but you follow the pattern. Okay, so let's go into, what is this one? There. So let's go down a little bit. Here's a good example. Let's do a different one. I want to find one that I'm looking for here. This one. Okay, so right now I'm looking at some problem. It doesn't matter which one, but look at this problem, okay? This is typical exam level difficulty. Notice there's a picture up top, lengths and angles. And then here is an FBD. Think if you tried to put both of these sets of information on the same picture, your work will be very confusing to yourself. Now, do notice that sometimes you have to have the angles in here, but I don't have all the lengths in here. And so I have a separate picture with lengths and angles, and this one is basically forces and angles. You don't want to make the mistake of thinking that a length is a force by accident. It gets really complicated really quickly, okay? So if you have any questions about that, let me know. But that's what I'm talking about when I mean two separate pictures. I cannot emphasize that enough, and I have, whoops, I've emphasized that now, okay? So let's get back in there. All right. Now, this is not always the best way to do it. It's almost always the best way to do it, okay? So usually we're going to do, I just want to emphasize this, do torques, then do a force problem. So you're so used to doing forces from chapter 5 and 6, and you got really good at it. Awesome. But I want you to do torques first. Why? Because it's usually easier once you get used to it. So notice when you're doing sum of torques, I want to stress something here. Okay? Because its rotation is 0 about any point, you choose the pivot. You get to choose because it's not rotating about any point. Okay? That's huge. So there's a tip. When you're choosing your pivot point, I'm going to go to my other problem here. You could choose a pivot point. Whoops, sorry. When I choose the pivot point, I'm going to give the screen a second to catch up here. All right. So notice this is I'm looking at this FBD right here. I'm looking at this FBD right here. I could choose any point I want. I could choose this point, or I could choose this green point. I could also choose this purple point or this pink point. And notice those are the 4 logical pivot point choices for this problem. The main benefit of choosing a pivot point, any force whose line of action runs through the pivot drops out of the torque equation. Okay? So for example, if I choose this, whoops, if I choose this pivot point, notice Rx and Ry contribute no torque. So that's why you start with the torque equation. We can forget about the torque due to Rx and Ry. And notice right here is my torque equation. We'll discuss this in a minute. It looks like a bunch of blobs of crap right now. But I want to point out, notice that Rx and Ry do not appear in my torque equation because I chose this purple point as the pivot. So you're going to choose a pivot point, and I want you to choose it wisely so that you can eliminate forces and write easy torque equations. If you're not sure, you could actually do it for every single one, and you could write each one and see which one is the easiest to work with. And usually in most physics problems, one of them jumps out at you as like, oh, this only has one unknown. Maybe I'll use that one. All right. Let's go back to right here. Okay. Figure out which forces cause no torques. Okay, so again, I'm looking through bullet 2. Do sum of torques, choose a pivot point, figure out which ones don't cause a torque, sketch the problem with only the remaining forces. Notice you have to choose a direction to call positive. In math class, we always call counterclockwise positive. In this class, sometimes we're going to do it the other way. Right, that's like calling sometimes we call up positive direction, sometimes we call down positive direction for physics. It doesn't matter. Coordinate systems shouldn't affect the results. All right. So list out the remaining torques and figure out each one. Always double check the angles, verify you drew the R vector correctly, check the sign. If possible, try to write your radius in terms of L. I'll explain that in a minute. And watch out. This is where we have 4 different methods for getting the torque. This one always works, but boy, it's slow. This one is very similar. It works, but it can be sometimes slow. This one is usually fast, but as you discovered at the last test, sometimes it's tricky figuring out R perpendicular. And this one is sometimes used. If you're a civil engineer or if you're an engineer of any type, you're going to be a master at this after you take an entire course in this page. So this gets so complicated, teachers teach an entire course in this page. All right. Then you do the sum of torques. Great. Now forces, just do the free body diagram. Oh, there's one thing that you need to watch out here. Everybody pay attention and put a star on this or something. Emphasize bullet 3B. You got to emphasize this. This is one of the more common mistakes students make. All right. The coordinate system for bullet 2, you have one coordinate system. But then when you do the second one, use a normal coordinate system. Why? Because that's what civil engineers do. Do it the right way or you're going to get lost. I do it that way too. So use normal XY. And by normal XY, I mean straight up and straight to the right. I mean X, Y. So for this part, you want to use a normal XY coordinate system. One of the things that happens is you need to split up the forces into components that might be different than the way you split them up here. So like, especially this, if you use this force perpendicular, well, if your rod is angled or something, right, the XY components might not be the same. Let me check if anybody's in the waiting room. Okay, there we go. I think I got it. Okay, at risk of boring you, I know I'm going a little bit slow here, but I want to emphasize this. Okay, it's really huge. This bold line here. Do not assume forces split up the same way. And let me see if I could give you an example really quick, okay? I'm going to scroll a little bit. I think that's, sorry, what I got to do here. I should do it this way. What's a good one for this one? I think 12.10 might be the one. And let me see here. This is a, okay, yeah. So I'm looking at 12.9 first, okay? So this is a good one to look at. I'm looking at the solution for 12.9. Okay, solution for 12.9. Page 104. Okay, and then I'm looking at the solution. I just want to emphasize, and I'm going to change the size of this so you can see a little bit. Notice I did 3 diagrams for this one. This is common. Okay. So one is for lengths and angles. Another one is for torques. And then look at this last one. Look carefully what I did differently here. Notice for this one, I drew the forces, and notice, I'll try and emphasize one of them here. The tension, I now split it into X and Y components like this. Okay, notice this R vector, that's the reaction force at the pivot. That's just the name for the force at the pivot. I split that into X and Y. And so notice you split the forces up differently if you're doing a torque picture versus a force picture. That's all I wanted to emphasize there. My apologies if that's really, really small on your screen, okay? All right, but so I'm going to stop that. Well, actually, let me go back to here and see if there's anything else before I pause the share. Okay, so after that, you have three equations: forces in the x, forces in the y, and torque. List them neatly, reread the problem, figure out what you're supposed to find, WTF. And if you, this is a rare special thing here. Sometimes if you don't have enough equations to handle it, you might consider doing another torque equation. All right, so that's listed there, but I don't think you're going to need that on exam day, but every once in a while you could do that. And then use your equations to solve. Hey, everybody, watch out. I cannot stress this enough either. If the problem says it's about to slip, then friction is mu static times the normal. But if you don't see anything in that problem that says that, you can't assume it's just about to slip, okay? So sometimes it's just F. Sometimes it's mu static times normal. Sometimes it's F. Sometimes it's mu static normal. And then this is kind of important. Check your answers. If for some reason you get a negative number for a tension or a mass, you did something wrong. However, if you get a negative number for Rx or Ry, that is fine. Think, if you draw Rx pointing to the right and you get a negative number, that's basically saying it's +3 in the negative I hat. So just kind of keep track of this for the reaction force. This is the buzzword I want you to, or the buzz phrase or whatever. If Rx or Ry is negative, your magnitude is correct, but the direction is opposite the direction drawn. So if you draw it pointing to the right, it actually ends up pointing to the left if you get a negative number. Here's my summary. Great. Blah, 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 blah. All right, I'm going to stop and see if there's any questions right now. Yeah. Sometimes it helps to know law of sines and cosines for sure. And negative tension or mass is a no. That's correct. I will say this, Jay, there's one exception to negative tension. If you have a rod instead of a cable, negative tension actually makes sense too. So imagine if you're building a bridge out of a truss. And I'm going to try and draw a picture here. So let's say I have a bridge like this. And then, sorry, it doesn't perfectly connect here. All right, and I'm going to keep it simple. Maybe this is the bridge. So you could imagine this is a bridge and it's sitting here on a roadway or something, and it's sitting on the other side on a roadway. So this bridge is just sitting there. The idea here is a negative tension actually makes sense. So let's say you assumed let's say you assumed this thing was being pulled this way. So there was tension. A negative would mean that this rod is under compression or something like that. So only in that case, where if you use a rod instead of a cable. Is that enough on that, Jay? You can have negative tension for a rod, but not negative tension for a string or a loose cable. Yeah. All right. Okay. Okay. We have both rods and cables. So I think at this point, maybe we could give some examples and start to look at them. Does that sound like a plan? I'm going to go for it. And then if it's not a plan, well, I guess we'll deal with it. All right. So let's see here. Let's start with the really simple one, this one. All right. So we have a plank of known length L supported by a scale on each end. So I'm looking at 12.1, and this one's a nice one to start because everything is either up or down. We don't have to deal with cosine and sine yet. Now I'm going to try and show you a demo of this, and if I fail, you can let me know, all right? So let me see if I can do this. This is really not my thing. Trying to think what I could do. to try and do a little better. Sorry about this. All right, so, oops. Okay, so we got support 1, support 2, and this is supposed to be the rod, right? So let me see. I don't know if you can even see that, but there. So, and let's see if I can put this up so you can see it a little bit better. Let's use this other piece. It's a little bit cleaner. Trying my best, people. All right. So there is supposed to be, this is the support, right? And then you put a human being on there like this. All right. And so the idea is if these supports are right at the edge, this cup is pushing up, this cup is pushing up, but maybe your intuition tells you if you put more weight on this side, this one's probably pushing up harder a little bit. And now what we could do is if this is a scale and we read this scale and that scale, hopefully what we could find is the center mass of a human. So normally I actually lay down on a board and we calculate my center mass. But for now, just hopefully this helps you visualize that a little bit. All right. And then let's go back and look at the problem. Whoops. Such a goofy system here. All right. So let me share the screen again. All right. So that was supposed to be a real life visualization of this. Hopefully that made some sense. And I'm going to stop my video to save bandwidth again. All right. So in this case, the plank is not rotating. We know sum of torques is 0 about point A. I want you to try and write down the torque equation for point A. And if it's been a while since you've done this, let's go ahead and use the solution, all right? So again, I'll make sure you read this. Plank has length L. There was a scale at each end. After the plank display, okay, da, 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 da. Okay, so notice this. We don't need to worry about the mass of the plank for this problem. Center of the person. Okay, so we're going to try and find the center mass of the person there. All right, part A. Let's go look at that one. Part A. There. So hopefully this picture makes sense to you. There's a normal force at position A. There's a normal force at position B. We discussed this a little bit. If I could just scoot this a little bit this way, we expect that the normal force at position B is probably going to be a little bit smaller because more of the weight is sitting on support A. All right. And then distance X from the middle is this person's center of mass. So now watch out here. This one might remember that there's going to be mg here. Now mg acts on the person. As a result of mg from the earth, we know the board is going to act upwards. I'm going to call this normal force P for normal force that the board exerts on the person. Maybe I'll say person and B for person and board. By Newton's third law, there's a reaction to that. So by Newton's third law, I know that there's a normal force this way. That's the normal force of the board person, which is the same because A equals 0. If A equals 0, the green arrow equals the red arrow. By Newton's third law, the blue arrow has the same size as the green arrow. And that is why I wrote mg here instead of normal force of the board person. Okay, technically this is the force that the person exerts on the board. The person does not exert mg on the board. The person exerts a normal force. However, because of what I just said, again, green equals red by sum of force equals 0. It's static equilibrium. Blue equals green because of Newton's third law. Okay, you're going to hear me use that a lot, and I'm trying to emphasize that because you have a final exam coming, and I don't want you to think that you can always just use mg. Sometimes with like boxes and elevators, the normal force was not equal to mg. Do you remember that? When you had an elevator and there's multiple boxes, sometimes N is equal to mg plus ma or something like that, or mg minus ma, depending. All right, you could throw questions in the chat anytime. Trey's there if you need help or whatever. But yeah, all right. Notice we've got our forces, and now I'm going to take a look at this again. Okay. Let me make that smaller. There we go. Okay, so what I just tried to tell you should be written in there, okay? So watch out for that one, okay? Great. And so here's the torque equation, all right? So if I use A as my pivot point, I'm using this point as the pivot point. Notice this term does no torque. So that's why down in here, the torque due to normal force A equals 0 because the line of action runs through the pivot for that force. Okay? And hopefully that makes sense, and I'm going to check the chat. Jay, I wouldn't say it that way. I would say if it's not accelerating, usually we can equate the forces between objects with the object's weight. So that's how I would say it. And I'll give you another example where it's kind of tricky. I tell you what, I'll give you another example later, okay? I have another example that we're going to do today, so let's deal with that then. But yeah, basically that you're just allowing, you could replace N's with MGs. Okay. Now, notice sum of forces. I think this is pretty easy. I think most of you have no trouble with the sum of forces right there, right? You got NA going up, NB going up, and MG going down. If we do this, notice I can rearrange and solve for X. Okay, X is something I don't know. That's the center of mass of my body. Or in this case, where I did a little demo over here, it was the center mass of the stapler. We wanted to find the center mass of the object. So if X is the unknown, L is usually known. Normal force is the scale reading. MG, I don't really know that right away, but I do know both scale readings. So notice that's why I wrote it this way. If I know the two scale readings, I can get the person's center mass. And it's usually around your belly button or something like that, okay? Now, I'm going to clear those drawings, and I'm going to stop for a sec, see if that makes sense. Okay, so no, generally speaking, this is all static equilibrium. However, where'd you go? Oh, I'm not even looking at faces, so it doesn't matter. Oh, there's Ryan. There are a few special problems where it's moving, but we could treat it as a static equilibrium problem if we use fictitious forces. So you may recall at the end of chapter 6, we said you could replace MA with a force and then set forces equal to 0, do a static equilibrium problem, and it's a really cool trick. Problems that are otherwise very difficult suddenly become easy if you use this fictitious force. And I'll show you one of those later. But generally speaking, on test questions, it's really obvious what static equilibrium is. You'll see something with a cable or a ladder, and you'll be like, or a ball at rest, and I'll say it's in static equilibrium or something. So yeah, okay, good. Other questions? All right, I'm kind of slow playing it, just trying to really go slow here, but it will pick up and you'll find that you can start kicking ass on these any minute now. So let's go back, and I want to read and show you that you can actually choose any point you want if my screen ever catches up. All right, so now look what I did here. And just to show you where I'm at in the question, let's go back to here. I want to do 12.1D, and I want to check the results using torques about point B. Remember, I told you over and over again, if it's not rotating, it's not rotating about any point. So we should be able to do this about point B. Okay. So let's go over there and look at that right here. So now what we're going to do, this is the pivot point. If this is the pivot point, notice the distance. This distance here was X. This was X. So this distance here is L minus X. I hope that makes sense because you know the whole distance is L. That's probably pretty straightforward. Now, notice what I did. Now I'm calling clockwise a positive torque. Why? Because who cares? It's all adding up to 0. So why not just call whatever I want positive? So you could have done this a different way. All that would happen is if you chose a different coordinate system, you'd get negative signs in this equation right here. Now, based upon this, take a look at the signs. I go over to this, mg, that's twisting it kind of downwards. That's going to twist it this way. That's a negative. So that's why this is a negative torque. This one would twist it in the positive direction. If I go all the way over here and then up, that's twisting it up. So that's why I got a positive for that one. So in case you're wondering where the plus and the minus signs come from, now you might be wondering, wait a minute, what did he do for the torques? Remember that torque is going to be R perpendicular times F, or you could also write it as RF sine theta. Now in this case, I just want to point out, if you use the pink method, this is a right angle, so is this. And so either one of these, for this case, you'd get 90 degrees. And that's why we don't have any sines or cosines popping up in here. Okay, and the same for this one, right? Everything was at right angles. And now, once you do this, you get the same result as before. Okay? By the way, there's a third obvious point. This might have been a smarter point. Look at this one. What if I did center of mass about this point, right? Or I mean, sorry, not center mass. What if I did the torques about point C? Take a second to write that down. It's going to take me a long time to write it down. So see if you could beat me. The sum of torques about C should equal 0. In this case, I'm going to use this coordinate system here. I'm going to use this coordinate system up here. So standard counterclockwise positive. So about point C, this one is going to rotate that way. This one is going to rotate that way. So let's see. I'm going to get NB times L minus X minus NA times X. And now this one drops out because line of action through the pivot. That's it. And notice this gets you to there without even having to do forces. So sometimes if you pick the pivot point wisely, you don't even need to do forces. That's a lot of stuff. So I'm going to pause for questions without deleting anything on the screen in case some of this makes some sense or you have questions. So I'm pausing for questions right now. Is this kind of making some sense? I have no idea if you're getting it. Oops, let me get that out of the way. Okay, I'm going to go ahead and stop the share for a sec. Just let me know if this is going too fast, too slow, or if it's making some sense. Just give me some feedback of any kind. If you're doing all right, let me know, okay? Okay. All right. Thanks for the feedback. So let's go ahead and try and go on to the next one. Does that sound like a plan? Or it seems like nobody had questions on that one because there's no angles. It's pretty straightforward. You don't have to think a lot. As soon as you get angles in there, it gets trickier. So we should probably do some problems with angles. All right, so let's go look. All right. You're going to work on this one in lab. So this is a question, if you haven't done it, maybe after tonight's class, if you're wanting to do a practice problem, this is the one I would do. So I'm going to kind of leave this for you to do, but I'm going to go to the next one, which is strikingly similar. It's a little bit different, but I think you'll agree it's very similar. So I'm going to do 12.2 and let you try and do 12.1 and a half. Okay. So if this helps, oh boy, I'm going to try and do a demo. So let's read through the problem and then I'll show you a visualization of this. You have a uniform rod. Left end of the rod is attached to a frictionless pivot. So by the way, this symbol is the standard engineering symbol for a frictionless pivot. If you see something that looks like this, that has a special meaning in engineering. That's a frictionless pivot, okay? That semicircular shape with the dot inside is a pivot, okay? Now, we're going to put a rod here and tie a string to it. And then the string connects to the same wall as the rod. And then I'm going to put an extra mass on top. Okay, so this is going to look a little bit screwy, but I'm going to try and show you this, all right? Worst demo ever. Okay, let's see if I could do this one. All right, so this is kind of crazy. We're going to put a mass on top of here like this. And the idea is, I don't know if you can see this, but my finger is supposed to be the pivot. So this finger down here is the frictionless pivot, right? And maybe I'll just do this. I think that worked better for the lighting. Whoops. All right. And so I've got this string and I'm going to support it like this. So notice I can raise or lower this, and it just so happens to be at this orientation. Where are we? There we go. So I can raise or lower it. And so we're going to do purely horizontal. Got it? And this stapler on top is the extra mass. And these are sparklers from 4th of July a couple years ago. So I'm sure they're really amazing. Does that mean I get corporate sponsorship for this stupid lecture? All right. Okay. There we go. So, all right, let's get back into the actual picture there and see if this is helping. Okay. So now there's the picture. That's what we were trying to demonstrate. Draw the FBD. Hey, everybody, here's something I want you to know. When I say FBD for chapter 12, do not draw a dot. So I'm going to tell you what I mean here. In a lot of problems, we used to draw a dot and do forces like this, right? And do stuff like that. I don't want that anymore. No. For chapter 12, you want to draw the forces at the point where they are applied. You want to draw the forces at the point where they're applied. Also, you want to be careful how you split up the vectors into components. I'm going to show you this one because it's important to me, all right? So I'm going to make this bigger so it's easier to draw. Give me just a second. Okay. Hopefully you can see this picture all right. I'm waiting a second to let the computer catch up. So now there is going to be tension, right? Whoops. It's kind of hard to see that. I'm going to undo that and make this a little bit thicker. There's going to be tension here. All right. And now there's going to be a force here. Technically, this should be a normal force, right? But we're not going to say that because it takes too much time to do physics problems. All right. So there's 5 mg. Why haven't I been using that stupid text box and these arrows for months? I don't know, but whatever. All right, so now there's the mass of the rod. The mass of the rod is at its center. All right, and that's just mg. Sorry for the italics. All right, and now hopefully, oh, and then I guess I should label this one too, right? Okay, I've got the tension over here. Whoops. Okay. My own screen is lagging up. All right, so that's fine. Are there any other forces while I check the chat? Think to yourself. Yes, yes, that's true. But I'm looking for the forces, Ryan. Nice, Phil. Yeah, yeah. Oh man. Okay, so yes, okay. There's a lot in here. So let me say this: the two normal forces cancel out, and it's again, I can't stress this enough. It's we know that there's A equals 0. Because A equals 0, the normal force from the plank on 5m equals 5 mg in magnitude. Then I know the normal force that 5m exerts back downwards on the plank is also 5 mg. So it's there's no shorter way to say it than that. It's that whole, these are equal because A is 0. These are equal because of Newton's third law crap. Yep. All right. And yes, there's one other force there. Special. So let's draw it in a different color. Let's use this dark blue for fun. Reaction force. There's a force at the pivot, right? And I'm wondering which way it points. So I want you to think to yourself, estimate which way you think it points. All right. Is it going to be up, down, right, left? Take a second to think, and then I'll draw which way I think. And don't forget, if you draw it the wrong way, you can still get the right answer. Just take your guess, all right? All right, and this is what I'm going to think. Well, I see that I've got two downwards force arrows, so I'm thinking it's probably got an upwards component. I'm going to call that Ry. Okay. And then it's got an X component. Think to yourself, if this rod is not accelerating, I hope you thought there's going to be a component this way, right? Because the string is trying to shove that plank into the wall, so I've got to push outwards on it, and I'll show you that in just a second. But so usually we would label it like this. Okay, and so there's the forces on this thing. And you can see that already it's starting to get pretty busy looking. And this is a right triangle. So if you have triangles which are not a right triangle, man, it gets really complicated. All right, so got it. In this case, Nate Dogg is correct. He could see immediately if he's doing sum of forces in his head, everybody. Look at Nate Dogg in the chat. He said, does Rx equal negative Tx? That's absolutely right, because take a look. I'm going to try and use a different color so I can annotate now, all right? All right, so like, look at this one. We see that there's a component this way that's T subscript X. And there's a component this way, which is T subscript Y. Now I want to point out, this turns out to be kind of confusing when you're doing a torque problem. I'll explain why in just a second, but he's saying Tx and Rx should be equal in magnitude, but opposite. And that's because all these other forces are only in the Y direction. So because there's only two in the X direction, these two have to have the same magnitude. Cool. Now I'm going to undo so I get some space here. Now I want to show you something else too. Oh, come on. Okay. I would split up tension like this. Okay. This is tension in the Y direction. And this I would call tension in the X direction. All right. So in this case, notice I'm still splitting up the force, but look carefully. What I'm doing is I'm putting all of the tails at the point where the initial force was applied. I think this is more clear than drawing Tx up here. Why? Because if I draw Tx up here, it's not wrong. It's just it's not on the rod. So you might be wondering, does it cause a torque? Okay. So if I erase this, and this, look at this one. I hope you see this. This one. Notice Tx, it's better to draw it down here because I can tell Tx causes no torque because line of action through pivot. The torque due to T subscript X equals 0. Why? Line of action through pivot. So that's why I like to draw it with both of the forces, both of the force components with their tails at the point where the force is applied. Whoa, that's dense. I'm going to pause for a second. Any questions about that? Any questions? Get a sip of water real quick. All right. It is a lot. And this is, yeah. And then by the time you do like 4 of these today and then do 5 more at home or something, you'll be like, okay, I kind of get the pattern. It's a lot of geometry. Let me do one other thing here. Again, I'm just going to try and go back to what we were looking at here and make sure you got it. So the idea, hopefully you can see this pretty clearly, right? If I'm pulling, let me get this cable shortened here. The idea is, if I'm pulling this way, my hand has to push outwards, right? So I have to push outwards to oppose the tension pulling this way. I also have to lift upwards just to fight back against gravity pulling down on everything. So I have to push upwards and outwards. All right, good enough. All right. Yeah, I kind of like it. And maybe it's just that I've been trying to figure out how to do demos easily. And then this came to me, I found some string. So it's more fun when demos get here. Yeah. And this is fun if you're a civil engineer too, right? So, yeah, this is your bread and butter as a civil engineer. And then you write computer programs like we do in lab to do all the work for you. It's kind of a fun thing. All right. Let's go and look at the solution to this one now and see if there's anything else. So again, we're looking at 12.2, 12.2. All right. And then just making this smaller so I can see again. All right. So FBD for the rod, we kind of did that. This we've already talked about. Write down the sum of forces and then also write down sum of torques. All right. So that's what we need to focus on. And then we do some crap. Okay. So, all right, you've got the problem in front of you. I'm going to bring up the solution. All right. So hopefully this is making some sense. And notice in this problem, I actually drew the picture to scale. So it's not perfect, but it's roughly to scale, I guess. All right. This gives you a better idea. So 5 mg is down and big. Mg is down at the center of the rod. Tension is going to be up and to the left. Look at this. The reaction force supports more of the weight than the tension. Think about that. If I could, this component is bigger than this component because the weight is kind of centered over on the left side a little bit. Okay, because the weight is over here on the left side, this one has a slightly bigger Y component. I don't expect you to be able to figure that out while you're drawing it, but a lot of times when I finish my picture, I'll go back and draw them. So if you're wondering how I'm able to get these to scale, it's because I do the whole problem and then I go back and I redo my pictures to try and make them more instructive. That's all. Okay, don't expect to draw them to scale. Just draw some arrow and hope for the best. Okay, so now notice what I did here. I did the same problem again. It's not like I just took this one and split it into components so I could see it better, right? Lots of pictures makes your time. If you draw lots of pictures, it seems like it's going to take longer, but you get done faster. Okay, I cannot emphasize that. Notice this force right here, line of action through the pivot, nothing matters for the horizontal forces, okay? So now here's the force equation. Here's the force equation in the Y. That's pretty straightforward. And notice I used a standard XY coordinate system there. And now here's torque about the left end. So that's torque about this point right here. This drops out, and this drops out. Agreed? Again, this drops out, and this drops out, all for the same reason, line of action through pivot. That's why I use that way to say it. And if I could, I'm going to scoot down just a tiny bit. It's this line right here. If you remember it that way, it works. So just do it that way, okay? Okay. All right, and then at this point, this is the hard part. Once you got that down, I think let's take a look at part. Oh crap! Look, this is supposed to be A, B, C. So the next part is D. I'll write down a note to myself to fix that. I don't know what happened there. Oh, Microsoft Word, autocorrect. I love you. All right, whatever. Okay, so clearing all that. Sorry about that. Now, so this is part D. Sorry about this. This is part D. So if we plug in XL over 4, notice what happens to the math. So if X equals L over 4, length drops. And so we get this unusual, we get, what do we get? 5/4 plus a half, which is 2/4. So that's that. Then this one, those are both negative. So what I did is I brought those to the other side, right? And then I flipped the sides here. And so from this, if we know the angle, I think we can get the tension. Or if you know, so if you know the angle and the tension, you could get the mass, et cetera, et cetera, et cetera. And so you could just do some math and plug it in. If you plug in some numbers, if I know this and this, I know what G is, I can get the mass. Got it. Piece of cake. And to be clear, this was part D, and I think this was part E, and I think that's all of that question. Oh, wait, oh, there we are. Yeah. I see. Okay, cool. What do you think? Stop that. See if you're doing all right. So far, so good. Any other feedback? Okay, yeah. It's kind of fun, right? I thought this would be a good way to end. So yeah, hopefully this is like, yeah, all right. We're feeling good. We know physics. All right. It's all right. All right. I'd like you to take a second to look at 12.3. Look at 12.3. And this is a conceptual question, so I'm going to pause for a minute and let you take a look at it, talk to your neighbor or chat back and forth or do anything you want. And so we're looking at 12.3, all right? And I'm going to bring it up on the screen, and I'm going to stop my video to cut lag. Sorry if I was forgetting to do that. Oh, whoops, that's a solution. Sorry. Whoops. There we go. And then I'll see. It looks like I may have just got, I don't know if somebody's asking me a question there. Maybe that's just boring email. So yeah. Okay. Everybody, here's a heads up. I saw this on the test, last test. Remember, weight is not M. What is weight? This happens in this chapter a lot. Whoops. MG is hopefully what you said, and I appreciate you throwing it in the chat. Remember, work is capital W, all right? So work is capital W, and weight, you got to remember that it's not MG. It's, whoops. Oh, gosh, what did I do? Okay, there we go. All right, so weight is MG, and mass is M, and weight and mass are not the same thing. Think of it this way. When you go to outer space, G goes down, so your weight changes, but your mass, that's the amount of material that comprises you. It's your resistance to changes in motion. That stays the same, right? It takes a lot of energy to move a mass, even if you're in outer space, right? Because you still have to accelerate that mass, where you could have no weight in outer space if you're far enough from all planets. All right. So, okay. Hopefully you're actually looking at this question and taking a second to think about it. I'll pause for a second. At least this one should be good. And I can't remember, but I'm pretty sure there's a conceptual question looks something like this, but with a different scenario on your final exam. So it's probably good to make sure you can at least do this one. And then I think I totally mixed it up and changed the picture or something, right? So, so you have to think a lot. But yeah, look at this one. All right. Here, there's a tension here. Oh, what a dick move by the instructor. I gave you the wrong angle. So this is 30 degrees. Remember, it's important to have the angle, and this one is 120 degrees. This is 30. Okay, I did that on purpose. So maybe you're wondering which angle you should use, and it's either this one or that one is the angle for torque. It's from the R vector to the tension vector. So if your tension's going this way, you either want to use 120 or 30. You do not want to use 60. Okay, watch out for that. So I'm going to clear that out. All right, and so in this case, ooh, this is kind of fun. Let's go take a look at it now that maybe I've babbled long enough. You've had a chance to look at it. So let me go to the solution. And this is critical. If you want to learn about the tension in the string, do sum of torques about some other point. You don't want to do sum of torques at the point where the string connects. To be clear, If you do sum of torques about this point, there's one force you will not learn about, and that's the tension, right? So we do not want to use this. You might use this point, you might use this point, but you would not use the point where the string attaches. Otherwise, you can't learn anything. Also note, these problems are complicated enough. Rather than guess, I'm doing sum of torques instead of just guessing. I did not know, so I did the math. I did sum of torques really quick, and then I just figured it out. And notice you get wildly different results. And notice I use sine 30 degrees. I should technically have a 30 there. I mean a degree symbol there. Sorry about that. All right. And then I think from there you can rank them pretty easily. All right. So far, so good, I hope. I'll pause for just a second to let you get caught up. This is huge, the words. If you want to learn, think about your pivot point choice, because I chose my pivot point at the regular pivot so that I don't have to worry about the reaction forces. It's not that there aren't forces at the pivot. It's that by doing torque, they don't matter, and you can crank it out really fast. All right. Okay, enough on that. Let's go to part B. Okay, Nate Dogg already contributed. Oh, and there's a chat question. I'll get that. So Nate Dogg, don't say anything in the chat for part B. Okay, let's let everybody else get a shot at it. Okay, I'm waiting for my chat window to pop up. Come on. Oh my gosh, come on. Oh my gosh. All right, I'm gonna have to stop the share to see the. Oh gosh, it happens every time. Oh, MG. I'm not sure what you mean, Jay. Sorry, I got lost. What do you mean by that? You can unmute or you could just expand in your chat. I'm sorry, I don't understand.
That was him answering a previous question.
Oh, okay, okay. Sorry. And Jay's she. Okay. That's all right. Okay. Oh, got it. Sorry, my bad. My bad. All right. And so hopefully this one's not too bad. In which situations will it have a component pointing left? Well, let's think. This one. Why? Because the tension's pulling to the right. So in this case, if the string is pulling outwards, this reaction force is probably going this way. Now, this could be interesting. There's also, this might be crazy, but it's possible the reaction force is actually going downwards too. I have no idea. So think about it. You're going to have a weight here down, and now there's a huge lever arm. If you have a huge lever arm, this torque and versus, sorry, let me undo this. Let me start over. Okay, and I need to make this bigger so I have room to draw. This one is surprisingly interesting. It's also part C, okay? Part C asks this. So now if I could, okay, we've got a tension this way, and it's going to have to be huge because its lever arm is half the distance. So this upwards component, right, is going to be bigger than this downwards component. It's kind of hard to see. So I would expect, think about it like this. There's a huge lever arm for this one, so you have a small force. The lever arm for this one is half as long, so you need twice the vertical component. So now think about this. The upwards arrow from the string is bigger than the downwards arrow from the mass. So in this case, the pivot point needs to hold this down, but it also needs to go, let's see, about this far. like this. So the net force from the reaction force is like this. So in this case, you're actually going to get a downwards reaction force. You get a downwards reaction force, and I'm going to pause and let the screen lag catch up. Any questions about those arrows? And I'm going to assume you're doing all right there. Feel free, if you're still typing in the chat, to keep going. But now I'm going to clear this, and let's talk about this second part. So based off that, I want you to think, in which situations will they have that? And I'll try and answer the chat now, okay? The blue was due to the block. That was correct. The blue was due to the block. So if I'm not mistaken, there should be at least one other one here that has a downwards reaction force. So sometime, yeah, and then I'll let you think which one it would be. And then I'm going to go over and look at the solutions in 10 seconds. Here we go. I should add FBDs for these in the pictures, huh? So now look at this. This is cool. Check this out. If we want to learn about the reaction force instead of tension, do sum of torques about the string. That way tension drops out because its line of action goes through the pivot, and any horizontal force will not be in the equation, right? Because Rx still has that. So digest that paragraph, right? By choosing your pivot point wisely, you can learn all kinds of neat things. That's why you should redo 12.3 without looking at the solutions after I'm not around, okay? So it's just, you can learn a lot by choosing the pivot point wisely. By doing the pivot point at the string, and so to be clear, let's go look at it. So for part C, if I'm doing part C, if I choose these points as the pivot, I learn about mg and the reaction force. Now in this one, it's probably straight up, right? Because everything's straight up, right? And over here, everything's straight up and down. So this one's probably going to be straight down. And then for this one, I've got this screwball here. Oh, that one doesn't matter here. But so I did say this one was off that way already. And then for this one, we know this force is that way. This force has it downwards. So this one is going to have to be up and to the right. So hopefully that makes some sense. I'm going to pause there and see if that makes sense or any questions. All right. And so that was the hint. Okay, I'm going to pause. What do you think? This seems like a logical spot to take a break really quick, even though it's not 5:55, my favorite time. Yeah, I'm going to stop the live stream